Good evening to all, and welcome to the another session of the NPTEL course Heat Transfer. So today is the week 9 session, uh, and let's have a brief overview of what are the contents that are discussed in the week 9. So in week 9, it was a continuation from the week 8 topic, which was the heat exchangers. So in week 9, the NTU epsilon effectiveness NTU method, which is a uh, method for analyzing the heat exchanger, was discussed. So in the earlier week, that is a week 8, we discussed about the LMTD method, that is a long mean temperature difference. So why we need another method, that is NTU effectiveness method. So LMTD method we can only use when the exit temperatures or exit temperatures are known, or if say for example uh, if any of the exit temperature is known, we can use LMTD method because we can find the other exit temperature of hot or if we know either exit temperature of hot or cold fluid by the energy balance, we can find out the exit temperature of the other. But if both the exit temperature of either hot fluid or no cold fluid is not given, we cannot use the LMTD method. So that's why we are having a we have introduced or there is another method known as effectiveness NTU method. So that were discussed in the week 9 topic. That was the main discussion topic, and some of the tutorial problems related to the effectiveness NTU method was also discussed in week 9 content. So let's do some practice problems related to that NTU effectiveness method. Let's get started with the first question. So in this question, it's water with the CP, that is specific heat, is given at 80 degrees Celsius, enters a counterflow heat exchanger with a mass flow rate of 0.5 kilogram per second. And air enters at 30 degrees Celsius with a mass flow rate of 2.09 kilogram per second. If the effectiveness of the heat exchanger is 0.8, we need to find out the LMTD. So if you can see that the hot fluid and the cold fluid, both for both cases or for both fluids, there is the exit temperatures are not given. So it's not very easy to find out the LMTD method. So unless so that's why we are using the effectiveness NTU method. So let's so this the effectiveness is already given, so it's little bit comparatively easy. So let's see how we can solve this question. So if I graphically plot, so it's a counterflow heat exchanger. So the water is entering at 80 degrees Celsius and air is entering at 30 degrees Celsius. So TCO and THO are not given. Okay. So, so what is effectiveness? Given conditions are effectiveness. Effectiveness is given, that is epsilon, which is we already defined that as Q actual. It is the actual heat transfer that is happening in the heat exchanger divided by the maximum possible heat transfer that can happen in the heat exchanger. This concept I already discussed in the previous uh, session. So this is given as 0.8. Okay. So what is Q max? Q max is C min into THI minus TCI. This formula also we have discussed in the last week's session. So you can refer back if you have any doubt. And also this is discussed in this week contents also by the professor. So what if first we need to find out the heat capacities. That is C hot fluid. That is water is m dot water Cp of water. How much it is? 0.5 into 4.4180. So that is you get 290 joule per Kelvin second. Okay. Then C of cold fluid, which is air, that is also the mass flow rate of 2.09 into 1005. So this also when you calculate it will come out to be. So So it's which is the minimum value, which is C min, that is CH. So we are substituting this into THI 80 minus TCI 30. So that is 2090 into 50, which is how much it will be. It will come out to be 104500 watts. This is the maximum possible heat transfer that can happen in the heat exchanger. So effectiveness is already given. So we can Q actually is equal to 0.8 times 104500. So the actual heat transfer that is happening is 836. So I'm not, you can just verify the mathematics. Okay, so we got the Q actual. Now it's very easy to find out what are the exit temperatures of both fluids, that means both streams, that is hot fluid and cold fluid, because we find out what is the actual heat transfer. So just giving, that is 83600 is equal to, for water it is 2090 into 80 minus THO. So we'll get THO as 40 degrees Celsius, and same in case of the air side also, TCO minus 30. So the TCO will get us 70 degrees Celsius. So now we got the exit temperature. So now the LMTD is easy. We can write, that is delta Tm, block mean temperature difference, is delta Ti minus delta To divided by ln delta Ti by delta To. So what is delta Ti? That is Thi minus Tco, which is equal to, what is Thi? 80 minus 70, which is 10 degrees Celsius. Also T delta To, which is Tho minus Tci. Tho is 40 minus 30, it's 10. So both are 10, but so hence the LMTD in this case is not defined. So when the LMTD is not defined, so when the LMTD is not defined, means, so the when this expression for LMTD is not defined, we can, the LMTD of the heat exchanger, we can write it as either delta Ti or delta To. So the LMTD of this question is 10 degrees Celsius. Okay. So I hope this question was clear to you. Let's move on to the next question. So in this question, it's a parallel flow heat exchanger operating under steady state. The heat capacity rate of cold and hot, means capacities of hot and cold fluids are equal. The hot fluid is flowing at 1 kilogram per second with a specific heat of also given, enters the heat exchanger at 102 degrees Celsius, while the cold fluid has an inlet temperature of 15 degrees Celsius. The overall heat transfer coefficient is given, and the corresponding heat transfer area is also given. So we need to find out what is the exit temperature of the cold fluid. Okay, so it's a parallel flow heat exchanger. So hot fluid is entering at 102 degrees Celsius, and cold fluid is entering at 15 degrees Celsius. So both THO and TCO is not given. So what are the given parameters here? It is given that the CC, that is specific heat or heat capacities of cold fluid and hot fluids, are equal, and this is equal to 1 into 4000 which is equal to 4000 joules per Kelvin second. That is a given parameter. And the overall heat transfer coefficient U0 is given, that is 1 kilowatts per meter square Kelvin or 1000 watts per meter square Kelvin, and the surface area of heat transfer is also given 5 meters square. And to find is what is the exit temperature of the cold flame, TCO. This is what we need to find out. Okay. So how to start? So the exit condition of both the fluids are not given. We are not given the effectiveness of the heat exchanger like the previous case. So we have to actually apply the effectiveness NTU method. First we know yes, we have to find out what is the NTU, because number of transfer rate units. Which is UA by C min. Okay. U is given 1000 by C min. Here it's not C min because both the specific heats are same. So it will come out to be around 1.25. Now we have to use the expression for effectiveness of parallel flow heat exchanger. So this expression is easily available in any heat transfer textbooks like Incorpora or Senchen. So you can directly find out, and it is also derived in this textbook. So I'm directly writing this expression, that is epsilon is equal to 1 minus e raised to minus NTU into 1 plus CR divided by 1 plus CR. CR is equal to the ratio, that is C min by C max. In this case, both are same, so CR is equal to 1. So if you substitute here, it will become 1 minus epsilon times NTU into 2 divided by 2. Or we can write 1 minus epsilon raised to minus 2 NTU divided by 2. So this is the expression for effectiveness. So we can directly, N2 we know that is minus 2 into 1.25 divided by 2. So the answer will come out to be around 0.459. So now the effectiveness is we found out the effectiveness. Now the answer is the question is easy. We know it is epsilon is equal to Q actual divided by Q max. So Q actual is equal to epsilon times Q max, which is equal to 0.459 times C min. Here there is no C min, so both are same. So 4000 into THI minus TCI is 102 minus 15. So the answer will come out to be 159717.2 watts. Now just energy balance. That is 1597.2 is equal to 4000 into T is what is this TCO? TCO minus TCI. TCI is given so TCI is given which is how much 15 degrees Celsius. So from that we can directly find out what is PCI. So you can calculate it, and at last if you solve this expression, you will get the xt not TCO, sorry, it's TCO as 55 degrees Celsius. Okay, so this is actually how we use the effectiveness NTU method for finding out the outlet temperatures of a heat exchanger. When uh, when the exit none of the exit temperatures are given. Now let's move on to the next question. So in this question is a counterflow double pipe heat exchanger is to heat water from 20 degrees Celsius to uh, 80 degrees Celsius at a rate of 1.2 kilogram per second. The heating is to be accomplished by geothermal water whose specificity is different, available at 160 degrees Celsius at a mass flow rate of 2 kilogram per second. The inner tube is thin walled and has a diameter of 1.5 centimeters. If the overall heat transfer coefficient is 60 or 640 watts per meter square Kelvin, we need to determine the NTU and the length of the heat exchanger required to achieve this desired heat. So we have a counterflow heat exchanger. So geothermal water is coming at 160 degrees Celsius, and it is that normal water is being heated from 20 degree to 80 degrees Celsius. This mass flow rate is given as 2 kilogram per second, and this mass flow rate is given as 1.2 kilogram per second. Okay. And Cp is also given. So overall heat transfer coefficient U0 is given, that is 640 watts per meter square Kelvin. The inner diameter, the diameter is given, D is 1.5 centimeter. So we need to find out what is the NTU and length of the heat exchanger. Okay. So here from energy balance we can find out what is THO, that is energy balance. That is 2 into Cp of water is 4180 into 80 minus 20 is equal to, sorry, 1.2 into 2 into geothermal water 4310 into 160 minus TH. So if you calculate this, you will get the THO. But for NTU, so this is a parallel flow heat exchanger, right? So sorry, it's not, it's a counterflow heat exchanger. So the epsilon, so we can find out what is epsilon in this case, right? So actually in this, even the THO is not required, means finding out THO is not required. But even without finding that is exit temperature, we can solve this question. So, but just for your knowledge, you can just find out what is THO. So we can find out the epsilon, that is Q actual divided by Q max. That is Q actual is given 1.2180 into 80 minus 20. That is, which is C min. That is, we need to find out what is C min. Okay. So the hot fluid is 2 into 4310. That is volt per Kelvin seconds. And C uh, the cold fluid is 1.2 into 4180, which is 5016. So the Q actual divided by C min, that is, this is C min 5016 into THI minus TCR, that is 160 minus 80. Sorry, 160 minus 20. So if you find this out, you will get the effectiveness as around 0.4285. Okay, this is the effectiveness value. Now we have the equation for NTU for parallel counterflow heat exchanger. That I already told, we can refer to any textbook. What is the NTU and effective expression or relation between NTU and effectiveness for parallel flow and counterflow heat exchangers? I am directly writing this out. That NTU is equal to 1 pi CR minus 1 ln epsilon minus 1 divided by epsilon CR minus 1. This is for counterflow heat exchange. So what is CR? CR is C min by C max 5016 divided by 8620. You will get CR as 0.582. Okay. So let's substitute this here. Okay. So if you uh, substitute this value, you will get the NTU as 0.651. So the first part of our question is solved. So now it's easy because we know N2 is equal to UA by C min. Okay. Here A is equal to NTU into C min by U. That is NTU 0.651 into C min is 5016 divided by U, that is 640. Okay. This you will get it as 5.11 meter square. So just it is equal to 5 dl. So you will get L as 108. So this should be the length of the heat exchanger to achieve this temperature difference under this condition. Oh, I hope this was clear. So this is the uh, application of effectiveness NTU method. It's a question. There's a question of applying that effectiveness NTU method. So let's move on to the next question. So in this question, we have two fluids, that is A and B. which exchanges heat in a counterflow heat exchanger. Fluid A enters at 420 degrees Celsius and has a mass flow rate of 1 kilogram per second. And fluid B enters at 20 degrees Celsius, also has a mass flow rate of 1 kilogram per second. The effectiveness of the heat exchanger is 0.75. Determine the exit temperature of A and B. This is actually a similar kind of question we already solved. So, it's similar to the previous questions. So we have a counterflow heat exchanger. Just a minute. Okay, sorry for the disturbance. So one fluid enters at 420 degrees Celsius and has a mass flow rate of 1 kilogram per second, and other fluid enters at 20 degrees Celsius. The counterflow heat exchanger. Both have same mass flow rate. It is given, so it enters at 20 degrees Celsius. So the CPU values are also given. So the effectiveness value is given. That is 0.75. So to find out is THO and TCO are the two parameters we need to find out. So the epsilon is Q actual divided by Q maximum, which is given as 0.75 already. So what is Q actual? It is 0.75 into C min into THI minus TCI. Okay. So what is hot fluid CH? That is heat capacity. That is mass flow rate into CP. That is 1 into, that is hot fluid is CA. That is 1. That is 1000 joule per Kelvin second. And CB is equal to C cold fluid. That is m dot CP. 1 into 4000. That is 4000 joule per Kelvin second. So these are the specific heat capacity values for A and B. So the C minimum is this one, that is CMA. Is the CA, that is a hot fluid specific heat, is the minimum heat capacity. Sorry, heat capacity, yes. It's 0.75 into, this is C min is 1000 into THI, that is 420 minus 20. that is 0.75 into 1000 into 400. It will come out to be around 3000 kilowatts is the actual heat capacity. Sorry, here actual heat transfer of the heat exchanger. Now it's simple, just we need to equate this 3000 into 10 raised to 3 is equal to 1 into this fluid A 1000 into 420 minus THO. So THO will be 120 degrees Celsius, and for fluid B it is 3000 10 raised to 3 is equal to 1 into 4000 into TCO minus TCI is TCI 2000. So the TCO will be around 95. So these are the answers. So it's a very simple question, just continuation. Same question as like the previous question. So the answer to this question is option B, that is 120 and 95. So this is another question. A single shell pass, one tube pass counterflow heat exchanger has 10 tubes with inner diameter 10 mm and outer diameter 12 mm and length 1 meter. Saturated steam, dry steam, enters the shell side at a flow rate of 2 kg per second, temperature 1000 degree Celsius. The tube side, cold water enters at a flow rate of 10 kg per second with an inlet temperature of 25 degrees Celsius. The overall heat transfer coefficient based on outer surface area of the tube is 50 kilowatts per meter square cube. The specific heat of water is 4.18 and latent heat of steam is 2500 kilojoule per kilogram Kelvin. And what is the exit condition of the steam? So in this question, it's like condenser means steam is coming. The dry saturated steam is coming. So it's a phase change, not phase change. The temperature is constant because condensation is happening for the steam. So dry saturated steam is entering at 100 degrees Celsius, 2 kg per second. And on the tube side, we have the cold water which is flowing at a rate of 10 kilogram per second and 25 degrees Celsius. We need to find out what is the exit condition of the steam. Exit condition of the steam is we need to find out what is the quality X of steam at exit. This is the question. Okay. So the enthalpy of inlet steam, enthalpy of steam at inlet, that is m dot steam into hg. Hg is the enthalpy or the enthalpy of steam, saturated steam at 100 degrees Celsius. It's the pressure is saturated steam at 100 degrees Celsius. That is Hg. That is the we know in steam. I hope you are comfortable with the steam tables. You have the enthalpy of fluid and enthalpy of the vapor. So Like now it's a dry saturated stream, so there is no vapor content. Sorry, there is no fluid content here, so it's completely vapor. So we have the Hg, that is the enthalpy of the vapor, saturated vapor. Now enthalpy of steam at exit, it is exit, the heat will be lost. Means the cold water is taking away the heat, so there will be some condensation happening within the steam. It may not be entirely condensing, but a part of steam will be there. So in that case, it's like a wet condition. So we have some part of vapor and some part of liquid. Okay. In that case, how we are defining enthalpy? That is Hg plus X times HFG, right? What is HFG? Hg plus S times Hg minus Hf. So if we expand this, m dot s is equal to Hg plus X Hg minus X Hf. Okay. So this is the enthalpy of steam at exit. So what is the heat transfer? Net heat transfer. That is the heat lost by, that is the heat lost by steam. This is one minus two, right? So m dot s Hg minus m dot s Hg plus X times Hg minus X times Hf. So if I am writing Hg minus Hg plus X times Hg minus Hf, this cancels. So m dot s X Hg minus Hf, this is m dot X times H. So this is the heat lost by the steam. Okay. Now we doesn't know what is the exit temperature of the cold fluid, so we have to go for the effectiveness NTU method. So it's like a phase change is happening, right? So the temperature is constant. So this is a case. It doesn't matter whether it is parallel flow or counter flow. So the heat capacity of steam in this case will be infinity. So the CR, that is the ratio C min by C max, will be 0. In that case, the expression for NTU, expression for epsilon, that is the effectiveness, is equal to 1 minus e raised to minus NTU. So this is an expression you can for by heart. So it's like it's when a boiling or condensing, once phase change is happening, the effectiveness is equal to 1 minus e raised to minus NTU. Okay. So now let's find out what is NTU. It is UA by C min. So our overall heat transfer coefficient based on outer surface area. Okay. So we need to find out AO. That is, it is given 50 kilowatts pi into what is D. Outer diameter of the tube is 12 mm. That is 12 into 10 raised to minus 3 into length of the tube is 1 meter. Divided by C min, that is the mass flow rate of the heat capacity of cold fluid, which is water, which is 10. This we have to this okay. Each there are 10 tubes, so we need to, this is 10 kilogram per second is the total mass flow rate. So we have to divide this by 10. So the mass flow rate of a single tube is how much? or you can multiply the area by 10, because this here I calculate the area of a single tube. Like that we have 10 tubes. Okay, so either you can multiply this by 10, or you can divide the mass flow rate by 10. So both are same. So actually I am multiplying this by 10. So for total 10 into, so 10 into what is the 4180. So both will be cancelled. It doesn't matter whether you will multiply or it's yeah, because it is we are multiplying and dividing. You can take as a single case, or for the entire case. So the NTU will come out to be around 0.45. Now we got NTU. So it's easy to get epsilon, that is 1 minus e raised to minus 0.45. So this you will get it as, so the epsilon will get it as 0.3623. Okay. Now we know what is the Q actual, which is equal to epsilon times Q max. That is 0.3623 into C mean. That is how much is the minimum, which is the minimum. So it's total, right? So it's 10 to 4180 to 125. 25 or 20, 25. So this will come out to be the thing like 0.3623. So the answer will come out to be around 1135810.5 watts. This is the actual heat transfer. So now we are equating this equation 3 and equation 4. So equation 3 is equal to 4. So if we equate 1135810.5 is equal to mass flow rate of steam into X times HF. That is, mass flow rate of steam is given how much? 2 kilogram per second, and the latent heat of steam, that is HFG, that is it's also given, that is 2 into X into 2500 kilojoules. So you should be very careful with the units. One, three, five, eight. If we calculate this, the quality exit, we will get the X as 0.227. Sorry. Sorry, here I made one mistake here. This is not HG, this is HF. HF plus X times HFG. That is the right equation. Sorry, I made a correction here. Sorry. Says G minus HF is the uh, latent heat, that is, if I write HFG, it is answer is 1 minus x into HFG. Okay, this is equation number 3. So if you equate this, this should be 1 minus x. I'm sorry for the mistake. 1 minus x, and the x will come out to be around 0.7728. So this is the exit quality of the steam at the exit of the heat exchanger. I hope this question was clear. This was a little bit tricky question. So if you know steam, the steam table and all the steam cycle, how the we have to use the steam table and all. So it will be a very easy question. So let's go to the next question. A two shell passes and four tube passes heat exchanger is used to heat glycerin from 20 degrees Celsius to 50 degrees Celsius by hot water which enters the thin wall 2 centimeter diameter tube at 80 degrees Celsius and leaves at 40 degrees Celsius. The total length of the tube of the heat exchanger is 60 meter. The convection heat transfer coefficient is 25 watts per meter square Kelvin and 160 watts per meter square Kelvin. Determine the rate of heat transfer without fouling, and the properties are also given. Okay, so this is a special type of heat exchanger. It's not a single pass heat exchanger. It's a cell type heat exchanger with double multiple passes. So this will be like somewhat will be somewhat like this. So this is the actual heat exchanger. So hot fluid. This is two shell passes and four tube passes. Okay. So is used to heat glycerin from which enters the thin wall diameter tubes and hot water which enters 80 degrees Celsius and leaves at 40 degrees Celsius, and it is entering at 20 degrees Celsius and 50 degrees Celsius. Okay. So this is the schematic or of the heat exchanger. So it is given the convection heat transfer coefficient on glycerin side, on the glycerin and 160, and also on the water tile also given. So we need to find out what is U, that is the rate of heat transfer Q without fouling. Okay. So this is not a simple heat exchanger. It's a like a heat exchanger with multiple passes. So we cannot solve this using our direct expression. So we need to, the expression is fine, that is Q is equal to U A F delta Tm. Means this is same. We are adding an extra correction factor. Correction factor we need to add. And this correction factor we can find out from the graphs. That is, this is a graph I have taken from heat transfer by Sencher. So there are other graphs also for different kinds of orientation and all. As this is the graph we need to solve this for this question. Okay. So our only task is to find out what is f. Means our primary task. It's not the only task. Our primary task is to find out what is f. That is a correction factor. For that, we need to find out p. P and R. P is equal to T2 minus T1 divided by T1 minus T1. So here, for our case, the T1 is 20 degrees Celsius and capital T1, and capital T2 is 50 degrees Celsius. And also small T2 is 80 degrees Celsius. Sorry, not 80 degrees Celsius because it is entering, right? So if we draw according to this, okay. So T2 is 40 and T1 is 80. Okay. So every temperature are given. So we just need to find out what is P, that is 40 minus 80 divided by 20 minus 80, that is minus 40 by minus 60, it will become 2 by 3. Then what is R? T1 minus T2 by T2 minus T1. That is T1 is 20 minus T2 is 50. T2, small T2 is 40 minus T1 is 80 minus 30 by minus 50. That is that's 40. 3 by 4, which is around 0.75. So now we just need to, we got what is P and R. So from the graph, we need to find out what is the correction factor. Okay. So in from P side, it's 0.667. It's 0.65. So somewhere here. And from our side, it's we need to find out 0.75. So this is 0.8. So it will be somewhere in between this. So this 0.8 and this is 0.6. So it will be more close to like this. Okay. So the answer will be around 0.91. This is how we will use the graph. Okay. So the correction factor F is equal to 0.91. From graph. Now we need to find out what is LMTD, that is delta Ti minus delta To divided by ln delta Ti by delta To. that is inlet temperature difference. It is that is delta Ti is equal to Th in minus Tc out, which is equal to 80 minus 50, 30 degrees Celsius, and delta Tho equal to Tho minus Tc in, which is equal to 40 minus 20 is 20 degrees Celsius. So if we calculate 30 minus 20 by ln 30 by 20, you will get the answer as 24.66 degrees Celsius. Okay. So what is U? That is equal to, we know. So this expression we already find out 1 by Hi minus 1 by Ho. So here we are neglecting. So here we are neglecting the uh, uh, means fouling. So in the question itself, it is given that we need to uh, we can consider the heat transfer without fouling. So and also the thing it is given with as thin wall. So we can neglect the conduction resistance. So it's only the convection resistance which comes into play. So it will become 1 by Hi, that is 160, plus 1 by Ho is 25. That is inner heat transfer coefficient is given, exit heat transfer coefficient also given, outlet. That is, if you calculate U will become, you will get U as 21.612 watts per meter per Kelvin. So next, let's find out what is so we find out everything we required. So that is U. If we find out A, we already know. Then F we find out, delta F we know. So U is equal to UAF delta Tm. Okay. U 21.612, it is pi into D is given how much? 2 centimeter, and total length is given as 60 centimeters. It is 0.02 into 60 into F is 0.91 and LMTD is 24.66. Okay. So you will get Q, that is what we need to find out, that is Q, we will get it as 1830.35 watts. So this is the heat transfer for this heat exchanger. So let's quickly solve this question also. It's a simple question. So we just need to find out what is the if there is a fouling occurs, we need to find out what is the heat transfer. So U0 A F delta Tm. So only this heat transfer coefficient will be varying. So the rest of the things, that is F delta Tm A, everything will remain constant. So we need to find out what is U0, which is equal to 1 by Hi plus 1 by Ho plus Rf by, that is Rf. So 1 by H160 plus 1 by Ho 25 plus 0.0006. So if we found out U0 becomes 21.345 watts per meter square Kelvin. So you can see there is a slight reduction in the heat transfer coefficient. So let's see what is Q, that is U0 A F delta Tm. That is, if you substitute this, you will get 1808.74 watts. So there is a small difference, that is a difference of around 22 watts because of the reduction of heat transfer of around 22 watts is there because of the fouling. So here comes the end of our end of this session, and hope you hope you will find this section useful, and I hope you enjoyed this session also. So thank you very much, and we will meet in the next Monday, same timing. So have a nice week ahead. Thank you. Thank you very much.